Do we have visual? Oh, yes. There's a link to the slides up there if you want to follow along on something easy to read. But thanks for coming this morning to Kernel Mini-Conf. I'm going to talk about runtimes, language runtimes, the anatomy of language runtimes, and your contract with the kernel. This brief introduction as to who I am. I'm Curtis. This is a clearer picture of me if you can't see my face from where you are. I'm a research engineer. I work with the Trustworthy Systems group at CSIRO's Data61. And I'm part of the team that develops the SCL4 microkernel. And in my spare time, I like to write a lot of Rust. And in this talk, hopefully by the end of it, you'll have some idea how the concept of write once, run anywhere is possible, and how a programming language's runtime interacts with its build system and the operating system in which it runs in order to provide a portable interface to satisfy that guarantee. And how when you change what the operating system is able to provide, that affects the ability of the language to provide that guarantee. A brief overview of how we're going to get through all of that. I'll start with what is a runtime, look at how runtimes let us develop software for major operating systems, and then we'll strip away the operating system and slowly build it back up on top of a microkernel to get an understanding of the scale at which a language can provide us with these portable tools, up to the point where we can write user applications again. And then I'll briefly mention the work I've done with Trustworthy Systems that got me into this mess to begin with. So what is a runtime, or a programming language runtime? It is a component of the programming language toolchain, and it executes within the application. So for the purpose of this talk, I'm referring to everything that the programming language toolchain provides that is executing at the same time the application is. This can include components of the standard library or a monolithic runtime application itself. And these together work to provide a high-level interface that is consistent to applications programmed to it, that doesn't change as you move between platforms. Some features that runtimes tend to provide. Process entry and exit is the most fundamental thing that your runtime is going to handle for you and abstract for you. Runtimes will provide dynamic memory management capabilities. This can be via explicit mechanisms like malloc and free, and it can also be via more managed systems such as garbage collection. Your runtime will often provide multitasking primitives for you. This can be abstractions on threading mechanisms provided by your operating system, but can also be mechanisms that perform multitasking within the application itself before handing off anything to the operating system for blocking and synchronization. Your runtime may abstract over the concepts of process management, how you start new processes and communicate with them, and in general, communication between processes and threads, and synchronizing them over a scheduler. More broadly, your runtime will give you mechanisms to interact with the file system, open files, close files, write and read data, use them as communication between processes, or use them as persistent storage. Networking as well, communicating with other computers via a network, remote hosts, and a bunch of OS-independent utilities, string manipulation, arithmetic, maths. Often there'll be some kind of user interface. Usually this is just going to be the assumption that you can interact over a text interface via standard in and standard out. Sometimes your runtime knows enough about the system to provide you tools to set up graphical interfaces. There are three main ways that a runtime is able to provide these features to you. The first is via the toolchain. So as the application is being built, things can be analyzed, your code could be analyzed, or we could find files in the file system and embed those into the runtime itself to provide features. When the application is running, we can communicate with the operating system and offload the need to do work to that operating system. This can be things like process metadata about what the current process that's running, communication with other processes, and communication with services offered by the operating system. And then finally, there's just everything that the execution of the runtime is able to do itself. It can do work when called into explicitly by the application. It does work before and after main, process entry and exit. And if you have a higher level language that's running in an interpreter or a bytecode VM, it's able to perform a lot of work in the process of executing that application. Most of what I'm going to talk about today is this middle category, the operating system, and how we can offload work to that. To begin with, I'm going to give an example of what it's like to develop for a major operating system. In this case, I'm going to look at writing a Rust application to run on Linux. And in this case, our Rust runtime is able to handle process and entry and exit for us. It can provide us dynamic memory management primitives. We can do multitasking. In this case, Rust can provide us with runtime level multitasking, but we'll be looking at threading provided by Linux. A user interface in this case would be standard in and standard out should we use it. We can start new processes and communicate them using the command API. The file system, we can open files, create files. We can open network sockets using an interface in the standard library for creating network socket listeners and connecting to other computers. This is a simple file server that I've written in 2 functions, which should demonstrate some of the features of the Rust runtime. This is our main function. The first thing it's going to do is handle process entry for us. It takes the mechanism Linux provides for starting a process and uses that to initialize itself and then call this main function, which we've defined. And in this case, it's also going to handle any errors for us. If our program hits upon any errors, we're immediately going to return to the runtime. It's going to print a message and then exit. The first thing we're going to do is bind to a network address using a mechanism from the standard library for creating a TCP listener. And then we're going to listen to every new connection that comes into this network address and handle it. We're going to spawn a thread dedicated to handling each new connection. That thread is going to handle the request, throw away any errors, and then try and shut down the stream gracefully to close the connection. And then in our handle function, which is called in this new thread, it's going to start reading information from this network stream. It's going to read in a string, convert it to a path, validate that path, make sure it's correctly formatted. It'll check that the location of that file is somewhere in the subdirectory of the current location that this program is executing. It will then open that file and then just read the contents of that file out to the network. The easiest way to look at what mechanisms the runtime is providing to us here is to look at all of these imports. So our first line is networking, the networking module, which gives us our TCP listener to wait for requests and listen to them. And then the mechanisms to communicate via that TCP stream. Our second line is multi-threading. This is an abstraction over the threading mechanisms provided by Linux. I/O is a set of standardized interfaces for describing what an implementer would need to provide to allow us to communicate using bytes. This could be to files, to strings, to buffers, to network streams. We have an abstraction over path resolution through the path APIs here. And this generalizes the different ways in which operating systems handle paths. We have the process environment here where we try and determine which directory in the file system our process is executing in. And we have the ability to open files and read files. And this last line here is just a type alias to tidy up the error handling in Rust to make the program nice and compact. But with these few lines, we have a basic file server that not only runs on Linux, but it will run on most major OSs without any change to this code. So it'll run on Linux, Windows, Mac OS, FreeBSD, and I don't need to change anything that is written here. And this is pretty representative of a lot of application level programming across these operating systems. It doesn't do any graphical interface stuff. It's not web applications, but it covers most of the other cases. But what happens when we take away the operating system and we now have to interact directly with the hardware? What are we able to rely on? If we have a portable language, what is that language actually able to supply to us? I'm going to take the example of Freestanding C on top of this x86 platform. And I'm going to talk about the most general form of runtime we could probably provide here that assumes the least amount of about the hardware case possible. So it's going to need to handle process entry and exit for us. Our process needs to start somehow. It could implement some sort of dynamic memory management. It could have a statically mapped region for the heap. It could provide some multitasking primitives, but any mechanisms for blocking or waiting on signals and resuming tasks is going to be largely provided by the application. Communicating with the user is quite difficult at this point. There's a lot of ways it could be done. We could make assumptions about the serial interface and use that, but that would be baking a lot of stuff into our runtime. There's no concept of processes here. There's no file system here to interact with. And there's no network driver for us to assume exists so that we can create network connections. And the C standard specification doesn't even provide a networking API. For that, you need like POSIX. So this is pretty minimal. Our application from before clearly we couldn't just run it here. It would need a lot more work to provide features to this runtime, and we would need to be doing a lot more work within the application. So the next easiest step to take to provide just that little bit more abstraction is our microkernel. And to cover just what exactly a microkernel is, I think this quote from Jochen Liedtke, I hope I've pronounced that correctly, sums it up really nicely, in that a concept is tolerated inside the microkernel only if moving it outside the kernel, i.e. permitting convening implementations, would prevent the implementation of the system's required functionality. If I can take a component of my kernel and move it outside of that kernel as a user application, and I'm still able to construct the same system I could before, there's no reason that should be in the kernel. So our kernel has the most minimal responsibility over the system possible. We implement all of our system services outside the kernel as user applications. We have very small modular components that can be independently worked on and communicate over well-defined interfaces. And we also end up with a very small, trusted computing base. If I have an application that needs to, for example, communicate over a network, and it communicates with the networking component of the system, and that networking component doesn't depend on the file system component, then my application doesn't need to trust at all that the file system component is functional, that it's available, that it's implemented correctly, that it's not malicious. There's no dependency there. The microkernel I'm going to use today to describe things is SEL4, because that's what I'm familiar with, it's what I work on. And this is a brief description of some of the features that it provides for us. But primarily, SEL4 is there to guarantee isolation between user mode processes and to provide the mechanism for us to control how those can communicate with each other and how they are scheduled and the resources that they can access. But importantly, the kernel itself in this case isn't providing any policy as to how that is done. We use mechanisms to inform the kernel about what that policy should be. We've also formally verified it. The concepts that SEL4 has, firstly, is virtual address spaces. I can create a virtual address space. I can map in physical memory and device memory into any virtual address space for a user process. I can schedule threads that execute within that virtual address space. I can perform IPC and synchronization between threads executing in the same or different virtual address spaces. We have two mechanisms for this: endpoints for synchronous communication, notification objects for asynchronous communication. And then we also have some mechanisms for device I/O, IRQs, I/O ports. Tends to get a bit platform specific at that point. And then the policy for who has access to these objects and these resources and who can pass around access to these resources is encoded using capability objects and capabilities within CNode objects. But if this is the set of features that our SEL4 kernel provides to us, and we want to implement a system on top of it, what is our application going to look like with just this? In this case, the first thing that executes within an SEL4 is the SEL4 system is the initial thread. What is going to be available to that first thread? And at this thread, the application, the virtual address space regions are loaded into memory at the same time the kernel is by the boot loading process. Once the kernel has finished booting, it's constructed all of the objects, kernel objects required to support a single thread running. It's just going to jump straight to the entry point of that application. And then it's going to provide an address to that application and an argument register that says, this is the region in memory called the boot info region, which just gives it a whole bunch of information about the configuration of the system and the kernel. And then the initial thread is given capabilities to all of the resources in the system that are not used explicitly for the kernel. This includes the current thread and capabilities to all of the resources that were required to construct it. Capabilities to objects needed to schedule new threads within the system, to manage and create new virtual address spaces, and the capabilities to all of the system memory and the device memory in the system, and capabilities for performing I/O with devices. So our C runtime for this initial thread on top of SEL4, what is it able to provide to us? What can we offload to this runtime so that we don't have to implement it in our application? In this case, SEL4 is not abstracting over much hardware beyond what the platform specifies, the x86-64 platform. So we get process entry and exit. That's well defined for this initial thread. We have dynamic memory management. In fact, if our runtime takes control over all of the memory passed to it and all of the capabilities passed to it, it could manage a dynamic heap because it can modify the virtual address space of this initial thread. It can provide multitasking by abstracting over threading mechanisms in SEL4. It can use the memory provided to it to construct thread objects and to schedule those objects for us, and so we can have things blocking independently. We don't really have much of a user interface yet. We don't have any mechanism within SEL4 to directly interact with the outside world in an abstract manner. What we do have is just access to all of the devices and the ability to perform low-level I/O with them. We don't have any process management because we still don't have the concept of processes. That's something we're going to need to construct ourselves. We don't have a file system yet because there's nothing here to connect to a device or provide a virtual file system, and likewise with networking. So we're not doing too much better than what we had with an embedded environment as far as what we can offload to a runtime. But we will get there. Could we write a useful application just using runtime mechanisms on this initial thread? Not really. As we still don't have mechanisms to directly interact with the user or the outside world, there's not a lot that we could offload to the runtime. We have no mechanisms for creating or communicating with other processes. We could potentially use the debugging configuration in SEL4, which lets us print debug output to at least send a message to the user. And we could, in our runtime, specify how file I/O works. And using our threads, we could set up a thread using, with an implementation of a serial driver, and use that to be responsible communicating to the user and set up an interface that way. But that still requires us to do a lot of work in our application ourselves to start having more of a friendly, easy-to-use system. So what we should do now is take this basis for a system and start building an operating system on top of it. And so the first thing that we're going to have to do in our system is we're going to need to construct the minimal set of processes that's going to be required to allow us to write more general applications. And we're going to use the initial thread to construct these components. So one of the first things we might need is a serial server, set up a dedicated process for managing the serial device, and allow that to communicate with other processes to interact with the user. We can set up a shared in-memory file system. We could have a preset selection of files built into that gets loaded initially. And we can now use that file system interface from any of our other processes. We could set up a component that is going to be responsible for launching processes. It has access to the file system, and we can ask it to set up a new process with its own virtual address space and threading on our behalf. We would also probably want to set up a device initializer that is able to probe the hardware to find out what devices are there and go through our file system and initialize devices and subsystems using the applications that's stored there. And once all this is done, we tend to reuse this initial thread as a memory management service, as it has the authority over all of the remaining memory in the system. We'll make it responsible for managing the virtual address spaces of all of the processes, for managing the creation of kernel objects for the processes, and for performing large IPC operations between different applications, for anything that needs a large buffer of memory to be copied between applications for communication. So once we have this initial OS, what are we now able to, in our runtime, offload to this operating system? Well, it now has abstraction over a TTY. It can handle interaction with a user directly. We have process entry and exit. We have dynamic memory management from before. We have multitasking from before. But in the case of these two, these are now offloaded entirely. There is another process that's able to set up threads for us. There is another service that is able to manage our heap dynamically for us. We can now interact directly with the user. We may only have one application that's able to do this, but it can communicate with the serial server directly. We can get standard in and standard out. We have the ability to create new processes from our file system. We can specify to the process launcher, go and start this process, go and find bash and set it up and give it access to the user interface. We still don't have networking. or a full file system based on a hard disk, because we haven't loaded the drivers for those yet. And so how do we move from this point to having a full operating system? Well, the benefit of this is we now have most of everything we need to write applications in a portable language without having to do a lot of hard work ourselves. So most of the applications we start from this point can be written as normal user-level programs, even if they're providing low-level system services. And so the next few components we can start can be implemented a bit easier. Some of them, such as device drivers, might need more information and use low-level interfaces with the hardware. But our device initializer is now going to start probing for devices. It's going to start loading the drivers from the file system. As it loads more devices, it might find hard disks. On those hard disks, it'll find even more drivers and more components that it can set up. It'll start new file system servers. And our system is rapidly going to finish booting. And we'll start getting other OS subsystems. We'll get configuration. We'll be able to load configuration files from file systems. We will be able to connect to audio devices and start making sounds. We get graphic subsystems working. We can have a graphical user interface. We have networking subsystems now. We can now communicate with other computers on the network. We can start doing human interface. If we want to set up an actual graphical user interface, we can do that. USB, etc. We now have basically an entire operating system under our feet. The next question is, how do we take all of these disparate components and provide them to user applications henceforth? The concept I'd like to introduce now is that of OS personalities. It's not by any means a new concept. The example I'd like to give comes from this mechanism from the Digital Equipment Corporation. They developed a system on top of the microkernel back in the early 90s. And what this system would do is, much like our system, it would have a set of common low-level resource and service processes which were accessible to any application that started in the system. What they would then do is they would start up a personality server which would communicate with these resources and provide a single unified interface to applications that, user-level applications that started on that operating system. Now initially they set up a personality server that presented the interface of the old VMS server they were trying to emulate at the time. But they found that they could also provide personality servers that presented interfaces of different operating systems. They had one that presented the interface of MS-DOS and one that presented a Unix-compliant interface. And what you could do, given that all of these personality servers were using the same resources in the back end, was that they could all communicate with each other. You could open your shell, call into an MS-DOS program, pipe its output to a VMS program, and format that using columns, a Unix program. They would all happily communicate with each other. Windows actually currently uses a similar model presently of multiple personalities, but rather than having personalities implemented as servers, the library that is linked into an application as it runs determines which personality is going to interact with. They primarily use this to give a limited set of features to components started early in the system, which only need minimal resources, minimal other servers to communicate with. And then more complete processes in the system communicate with everything that exists at that point. They've also used this in the past to provide support for Unix and other interfaces over the years. So we may want to have this similar personality model. We may wrap all of our interfaces, all of our components into a single personality and provide that as a personality server to our applications. We abstract all of the services. We now have a single interface that all of our applications are programmed to. And in the case of any duplicated systems we might have started, we may have multiple file systems, multiple network interfaces. We may at this point decide to virtualize and unify them so that they are more accessible for our runtime. And so what user applications can we now run on our operating system? Well, if we wanted to build a C runtime that offloaded as much work to our personality as possible, we could do basically everything. Our operating system abstracts over the entire system at this point. That says Rust. Never mind. But it can run, we can now do process entry and exit as we could before, dynamic memory management, and multitasking as we could with a more limited operating system. We have a standard user interface. This might be to a serial device. It might be to a virtual utility typewriter, to a graphical terminal. We now have process management. We can just run processes that exist in our file system, which now includes all of our hardware devices. We can now start networking, open sockets for networking communication. So what we can do is if we implement a Rust runtime and the standard library and target it at our operating system personality, is we can just take the code that we wrote before for our file server, compile it using our implementation of the runtime, and it will execute on our operating system just as it would on any other major OS. But we may find at this point that we overlooked some assumptions made by the Rust runtime, or by the C runtime, depending on what language we're implementing. A few things that it might assume is that there is a single file system, or a single service, which is required to translate a string path into any file we may have access to. And if we have distinct file systems, the runtime may not work with that well. It may make assumptions about how we interpret paths. If we have weird semantics for path interpretation, it may require some coaxing to get it to understand the particular requirements we have for paths, or for operating system strings in general. If we are using C, for example, it might assume that we have its understanding of strings rather than maybe wide strings or more complex representations. We might have the assumption of a single or a primary network interface that is internet connected, or we might assume that it doesn't matter which of the network interfaces are available, we're going to be able to connect to anything every way. So the runtime may not give us mechanisms to select which interface we're going to connect via. This might need to be resolved. It might have assumptions about how processes are created. It may assume that we're going to start processes by giving them particularly formatted strings in a particular fashion. We're going to pass additional argument and environment variables of strings. And once the process is created, we get pipes for standard in, standard out, and standard error. And this is a pretty general assumption. And if that's not how we have implemented processes, that's not how processes start for our system, it's going to be hard to get this portable runtime to agree with our system. So this is stuff that could be an issue when deciding on what your OS personality is, when deciding what your portable language runtime is going to provide as an interface, or when you're just implementing the runtime that matches the two. My final notes here are some of the work I've done with trustworthy system at runtimes, which got me thinking about all of this in the first place. I implemented a thing called the SCL4 runtime to solve a few problems we were having with supporting all of the platforms that we do. It's a non-standard C runtime. It's very incremental progress over what we had previously. It doesn't implement much. It just implements enough for us to do everything that we need to do on a day-to-day basis. It was primarily targeting applications that were running on SCL4 without the assumption of any sort of underlying operating system or standard interface with an underlying operating system. This even meant that it's not necessarily targeted at a root server, where we can assume we have all of these resources provided to us at startup. But it's enough to let us build and run all of the systems that we do at trustworthy systems on all of the platforms that we support. And it could be the basis for further runtime development as we have more complete systems to provide interfaces to. Its current features, very minimal. It provides process entry, so we can start a process. If you have constructors, dynamic initializers in your libraries, it will run those for you. And if you're running multiple threads in the same application, it will initialize thread local storage for your first thread. And any subsequent threads, it provides mechanisms for your thread creation libraries to initialize TLS there. Hopefully, at the end of all of this, you may have a better understanding of how the concept of write once, run everywhere is possible in many cases, how it relies a lot on the build process and primarily the operating system to provide features to your application, but how if you make big changes in your operating system or your operating system doesn't provide features, your programming language may not necessarily be as portable as it advertises itself. Any questions in what little time remains?
Do we have any questions?
If that's a no, then thanks.